Hey, what's up, everyone? Welcome to States of Matter Part 4. Today's all about gases, so we're going to go over the ideal gas law, diffusion, and effusion. Let's start off by looking at a molecular model of what a gas looks like. So these are going to be, super spaced out as compared to liquids or solids. They're going to be all constantly in motion, but you can see not all of them are going to be moving at the same rate. Some of these are going to be moving quite slowly, while some of these are going to be moving really fast. But basically, you just need to take away that they're like super spaced out and they're like in constant motion. We'll get more in depth into how they really behave a bit later on. All right, let's take a look at some of the properties. First of all, indefinite volume. You can take a container of gas and you can make it smaller. You can compress gas, and that is an important property of gases. Secondly, we have indefinite shape. Just like a liquid, gas is going to fill the shape of the container. Third, it's going to mix completely with other gases. So, in things like liquids, if you mix water and oil together, they're not going to mix completely. But, in gases, they are going to mix completely. Number 4 is that gases exert pressure on surroundings. So, whenever you're blowing up a balloon, what those gas particles are doing is that they're constantly exerting pressure on the rubber of the balloon. And that is what's working to blow up the balloon. In fact, that pressure that we call that gases exert, we just simplify it as pressure. And pressure can actually be measured. So if we're trying to measure something like atmospheric pressure, you can use a barometer. Basically, atmospheric pressure exerts some pressure on the mercury on the bottom here, and that brings the mercury up. And based on that, you can read the measure. But mercury can actually be measured in many units. You can use millimeters of mercury, which is also called torr. You can do it in atmospheres, bars, pascals, and you have like a conversion here. Usually the ones I would know is that 760 torr equals 1 atmosphere. Usually you're going to be using atmospheres, but I guess it's good to know that others exist. When learning about states of matter, a lot of people start with gases, and it's usually because the properties of gases and the behaviors of gases can be mathematically represented using gas laws. And so there are 3 really major ones. First of all, Boyle's law, which correlates pressure and volume. Charles' law, which correlates temperature and volume. And Avogadro's law, which correlates the number of moles and volume. So let's take a look at, first of all, Boyle's law, which tells that at constant number of moles and temperature, pressure times volume is going to equal some constant. So what does that mean? Say you have a container of volume V on the left here, and the pressure in that volume is going to be P. What happens when you now move that to a container that has twice the volume? What happens is that the pressure is cut in half. So if we multiply the pressure times the volume, for this first container, it's going to be P times V, which is just PV. But in the second container, you see that it's going to be 2P times 1/2 V. You're still left with PV. And so Boyle's law tells us that as you increase volume, you decrease pressure proportionally. So in other words, volume is proportional to 1 over P. As you increase volume, pressure decreases. Let's move on to Charles' law, which tells us that at constant number of moles and pressure, volume over temperature is going to be some constant. So again, let's look at a diagram. Let's say you have a volume V, and it's at some temperature T. If you double the volume, the temperature is 2T. Again, if you're trying to preserve pressure and the number of moles, you would need the pressure to be 2T. So if we did volume times temperature, we would get V over T. And then in this case, if we did volume over temperature, which is 2V over 2T, we would get that is also V over T. And so that's what this relationship is showing us. B is some constant. And so what Charles' law tells us is that volume is proportional to temperature. As you increase volume, in order to preserve the same number of moles and pressure, you also need to increase temperature proportionally. Let's look at the last one, which is Avogadro's law. So Avogadro's law tells us that at constant temperature and pressure, the volume over the number of moles is a constant C. So again, let's look at the diagram. Let the volume be V, and the number of moles be N. If we're trying to, if we double the volume of the container while keeping a constant temperature and pressure, the number of moles that we would need is 2N. So again, our volume times volume over the number of moles is V over N. And for here, it's 2V over 2N. So we were left with V over N. They are the same. And so in other terms, volume is proportional to the number of moles of your gas at constant temperature and pressure. And so let's summarize these laws, and you can see them in their proportionality form. And as it turns out, you can combine all these laws to create the ideal gas law. And this is something that once you learn, I don't think you'll ever forget. Pressure times volume equals the number of moles times R, which is a constant, times temperature. Usually, you're going to be using this, this value of R, but depending on what units you need, the value of R can change. So sometimes you might be using 8.3145, and in other terms, you might be using 0.082057. It is up to you to know which value of R to use in each scenario, but don't worry, we're going to do a bit of practice, and hopefully you'll learn like which instances you should use which. I do want to derive the ideal gas laws from our three laws though. So we have volume is proportional to 1 over P, we have volume is proportional to T, and we have volume is proportional to N. If we combine all these, we're going to get that volume is proportional to N times T over P. And so when you are dealing with a proportionality, you can turn a proportionality into an equation if you introduce some constant. So the constant, let's say it's some random constant, and we say volume equals R. R is our random constant times N over T over P. If we do a bit of algebra, we can get that V times P is R and T. And if we just move some terms around, we get PV equals nRT. So the point of R is to change this proportionality into an equation. And they have experimentally determined the value of R. And maybe you've even determined the value of R from like a chemistry class or some experiment that you've done. But this is where the ideal gas law comes from. But a gas that obeys this formula is called an ideal gas. You need to remember that an ideal gas is hypothetical. So as real gases approach low pressure and high temperature, they become more ideal, but no gas is truly ideal. We'll see why that is in a bit. But remember, any gas that correlates with this formula is called an ideal gas. Usually whenever you're looking at a gas problem, you can assume that it's ideal, but this equation does not perfectly map the actions of real gases, only ideal gases. All right, let's do some practice involving ideal gas laws. So a sample of neon gas is held at 25 degrees Celsius and 1 atmosphere in a cylinder with a movable piston. Under these conditions, the gas occupies 5 liters. What volume does the gas occupy at 12.5 degrees Celsius and 1 atmosphere? So let's write out our PV equals nRT. We know our pressure. Our pressure is going to be 1 atmosphere. Our volume is 5 liters. We don't know N. We know that the R here is going to be 0.08206. And temperature, you need to remember that temperature is in Kelvin. So please don't use Celsius. If you don't know how to convert Celsius to Kelvin, you just add 273 to the Celsius value. Really, it's 273.15, but I mean, people just say 273. And so you have 298. So times 298. And now we are trying to see under these conditions, what volume does the gas occupy at 12 degrees Celsius and 1 atmosphere? So let's write out the PV equals nRT for that. We know that the pressure is going to stay the same. We're trying to figure out the volume. We don't know N yet. We know R is going to be 0.08206. And we know that the new temperature is going to be 12.5 plus 273. And that's going to be about 285.5. So 285.5. Essentially, if we figured out N, we could solve this entire equation. So we can easily determine N by doing a bit of algebra here. So 5 over 0.08206 times 298 equals N. Let me just plug that into my calculator. So 5 divided by 0.08206 times 298. N is going to be about 0.204. And so now if we plug 204 into this, we're going to get that volume is equal to that N value times 0.08206 times 85.5. And so volume is going to be 4.79 liters. And we are complete. The answer was 4.8. I guess I suck at sig figs, but yeah. If you saw this on the real test, I guess you would just pick 4.8. But I hope you understand that PV equals nRT is actually really important, because if you know certain properties about the conditions of a gas, you can figure out some other properties just by doing some simple algebra. Okay, I think I have one more. A sample of an ideal gas has a volume of 0.5 liters at 25 degrees Celsius and 1.2 atmospheres of pressure. What is its volume at 75 degrees Celsius and 3.60 atmospheres? So let's set up our PV equals nRT. Equals nRT. We know our pressure is 1.2 atmospheres. Volume is 0.5 liters. We don't know N. We know R is 0.08206. And we know temperature is going to be 298, because remember 25 degrees Celsius is 298 Kelvin. And so if we solve for N, we're going to get that it's about 0.0245. And now let's see what the question is asking us. It's asking us what is the volume at 75 degrees Celsius and 3.60 atmospheres. So let's set up PV equals nRT again. We know that the pressure is 3.60. We don't know the volume. We know N is 0.0245. We know R is 0.08206. And we know that the temperature is going to be 75 plus 273, which is 348. And so now you can solve for V. And once you do so, you're going to get that V is about 0.195 liters. And that is our answer. There we go. We were right, and that was answer choice B. So again, you can see how if you know one state of the gas and you figure out like a property there, you can figure out more properties if you know like certain other conditions. Okay, let's move on to kinetic molecular theory. So at STP, which is standard pressure and temperature, 0 degrees Celsius and 1 atmosphere, the molar volume of an ideal gas is 22.4 liters. And so you can see some of these molar volumes of real gases, and you see that they edge on 22.4. We'll see why there are derivations in this a bit later. But let's take a look at kinetic molecular theory, which ties into STP and the molar volume. So kinetic molecular theory is a model that attempts to explain properties of an ideal gas. And it has a couple of postulates. First of all, the volume of individual gas particles is assumed to be 0. So the volume of like a gas is, like the actual volume of a gas particle is negligible. 2, the particles are in constant motion. Pressure is caused by the collisions between the gas and the walls. So particles always in motion, you're not going to find them standing still, and collisions are what cause pressure. 3, collisions between particles are elastic. So if two particles clash, they're not just going to stop. What they're going to do is that they're going to bounce off, and no energy is going to be lost between them. The energy transfer is like 100%. Number 4, the particles neither attract nor repel each other. So that means that there are no intermolecular forces. The reason that these derivations happen, is that in actual real gases, you are going to have some intermolecular force. And so these intermolecular forces are what keep them together. In ideal gases, we assume the intermolecular forces to be 0. The last postulate, I guess, is that average kinetic energy is proportional to the Kelvin temperature of the gas. And let's take that into more depth. By the way, if anyone can geometrically prove to me that this line in the middle here is straight or not straight, I will be forever grateful. PowerPoint doesn't tell you whether lines you draw are straight or not, so like this has been driving me crazy. Anyways, number 5, average kinetic energy is proportional to the Kelvin temperature of gas. What does that mean? If we look at the formula for average kinetic energy, so how fast gas particles are moving, we see that it is equal to 3/2 times the gas constant times temperature. And so the R here, by the way, is in the different value. It's 8.3145, not 0.08206. Well, as you increase the temperature, these molecules themselves are going to have more energy. And as you have more energy, they can move faster and faster, and that is kinetic energy. So as Kelvin temperature increases, so does the average kinetic energy, and the exact amount that it increases or decreases by is mapped by this equation right here. And let's do a bit of practice with that. What is the average kinetic energy of a sample of helium gas at 33 degrees Celsius? So kinetic energy is going to equal 3 over 2 times the ideal gas law, or gas constant rather, which in this case is 8.3145 times the temperature in Kelvin. So remember, the temperature in Kelvin is going to be 273 plus the Celsius temperature. And so if we plug this into a calculator, which I'll do right now, 8.3145 times 273 plus 33, we're going to get that the kinetic energy is about 3A16, and it's going to be in joules. And we were correct. Well, I didn't put the 4, whatever. But essentially, this tells you the energy, like the pure energy, the number of joules that a sample of gas is going to have at a certain temperature. And what's interesting about this equation here is that it has nothing to do with what sample you use. So this would be the same for a sample of helium gas, for a sample of hydrogen gas, anything. And so this shows kinetic molecular theory at work here. Since under kinetic molecular theory, all gas particles are assumed to have a volume of 0 and no intermolecular forces, there really isn't much to differentiate between different samples of gas. And so when calculating kinetic energy, it does not depend on what sample of gas you use. So we got our answer in joules per mole. I should really add a mole here. But what if you wanted the actual speed, right? We can get the speed using the root mean square velocity formula, which is the square root of 3 times r times t times the molar over the molar mass in kilograms. And you have to remember that the molar mass is in kilograms, and the gas constant is 8.3145. So let's take a look at a problem. What is the root mean square velocity of a sample of hydrogen gas at 100 degrees Celsius? Well, the root means velocity is going to equal the square root of 3 times r. R we know is 8.3145 times the temperature in Kelvin, and 100 degrees Celsius is going to be 373 degrees Kelvin, and that's going to be over the molar mass in kilograms. Well, we know that hydrogen gas is H2, and so that's going to have a molar mass of 2 grams. But 2 grams is 0.002 kilograms. So that means in order to determine root mean square velocity, we would need to evaluate this expression, which let me just do really quickly. And so if you were to evaluate, you're going to get that it's going to equal 2156.8, and the units are going to be in meters per second. So in this one, you actually do get the speed, as opposed to the other one where you got it in energy. And we were correct. So again, you need to remember that in both of them, the gas constant is going to change. It's not going to be 0.08206. It's going to be 8.3145. And at root mean square velocity, you have to use the molar mass in kilograms. Okay, let's do some problems before moving on. The kinetic theory of gases assumes all of the following except, so this is kinetic molecular theory. A, gases are composed of particles in random, ceaseless motion. Well, the kinetic molecular theory does assume that, so that's not true. The sizes of gas particles are negligible compared to the size of the container. That is true. We basically said that the volume is 0. Gas particles do not interact or repel each other. That is also true under kinetic molecular theory. And when gas particles cannot collide, kinetic energy is lost. That is not true under kinetic molecular theory. Remember, collisions are elastic. So when two particles come together, their energies transfer onto each other. And so under kinetic molecular theory, no kinetic energy is lost. And so it's going to be D, and we are correct. Let's go on to the next one. Under what conditions will the behavior of a real gas best approximate the behavior of an ideal gas? So we have high temperature and high pressure. Remember, a real gas is going to be moving really fast and the volume is going to be negligible. That is characteristic of high temperature because remember, under high temperature, your kinetic energy is going to be really high. And so one is definitely going to be it. But does high pressure mimic an ideal gas? Remember, high pressure is going to be the amount of force that each particle is going to be hitting the boundary, so whatever container that you're in. And high pressure is going to mean that the gas molecules are going to weigh a lot. But that is exactly the opposite of what we want for an ideal gas. Under an ideal gas, they're going to have zero volume. So really what we're looking for is high temperature and extremely low pressure. So 2 cannot be it. Therefore, the only answer is 1. And we're correct. I think we have 2 more. Under what conditions does the behavior of real gases deviate most from that predicted by the ideal gas law? So this is basically asking us the opposite of what the last one asked. So remember, under high temperature and low pressure, you're going to have as close to ideal gas as you get. But in order to deviate, you need to have the complete opposite. So low temperature and high pressure, which is B. And we're correct. Last one. Argon and helium are both gases at room temperature. How do the average molecular velocities of their atoms compare at this temperature? So this is going to involve us using the root mean square velocity, RMS, which is going to be square root of 3RT over the molar mass in kilograms. And so if we're keeping the temperature constant, let's just say for both of them the temperature is just 1. Just to simplify our calculations, even though it says room temperature, let's just simplify our calculations by just assuming that it's 1. First, let's do argon. So argon is going to have root mean square velocity, so 3 times 8.3145 times 1. Again, we are comparing the 2 values. So really, we're not looking for temperature here. Temperature is insignificant. We are just here to compare the values. And the molar mass in kilograms is going to be right about 40. So we can put 0.04. And then that's going to give us a value of about, so it's going to be about 24.97. Again, this is not the real value. I hope you understand this is not the real value. We are just doing this to compare the 2 values. And so if we look at helium, it's kind of messy, whatever. 8.3145 over the molar mass of helium is about 4. So that's going to be about 0.004. And you might already see the pattern, but let's do the calculation. This is going to be about 78.97. And so what is the relationship between these two? Let's say this value is A and this value is B. And so B is going to be equal to radical 10 times A. Because remember, this value is going to be 10 by a factor of 10 less than this. And so what is radical 10? What is radical 10 is right about 3. So B equals about 3A, which means that the velocity of helium is going to be about 3 times the velocity of argon, which is answer choice C. And we are correct. Let's move on to diffusion. So imagine you have a some gas sample in a container, and it is split by a divider. And then you get rid of the divider. So what's going to happen is that the gas molecules are going to disperse all over the entire container. And at the end, they're going to be evenly distributed throughout the entire container. And that is what diffusion is. It's kind of like, if you use like an air freshener. And on one side of the room, it's going to take a while for the gas particles to go all the way to the opposite side of the room, but it does happen. And so there's a difference between diffusion and effusion. In effusion, there's a divider, but there's a gap. And in that gap, the gas particles are going to start to flow through, and eventually there's going to be the same amount of gas particles on the left and right side. There's going to be an even distribution. And as it turns out, this diffusion and effusion, the rate of them, can be exemplified using this formula right here. So the rate of diffusion of one gas over the rate of diffusion of another gas is going to be equal to the square root of the temperature of the first gas times the molar mass of the second gas over the temperature of the second gas times the molar mass of the first gas. It's kind of a mouthful. So let's do a bit of practice with that. A gas diffuses 1/3 as fast as O2 at 100 degrees Celsius. This gas could be So the problem tells us that a gas is going to diffuse as 1/3 as fast as O2. So that means if we take the rate of diffusion of our gas, let's say that's x, over the rate of diffusion of O2, that's going to be 1/3. And so this tells us that 1/3 is going to equal temperature of the x times the molar mass of the O over the temperature of the O times the molar mass of the X. And so since they're both at 100 degrees Celsius, we can cancel the temperatures out. So essentially we're looking at 1/3 equals the molar mass of oxygen, which we know is 32 since it's diatomic, over the molar mass of X. And so if we square both sides, we're going to get that 32 over the molar mass of the random gas is going to equal 1/9. And so if you do out the math, it's going to be the molar mass of X is going to be 288. And so which one of these gases is going to have a molar mass of 288? Well, it's going to be D. C5F12 because it has the molar mass that we need. And it is correct. I also want to show the derivation of the Graham's law of diffusion because it is very much tied to root mean square velocity. So the rates are going to be proportional to speed. So R1 over R2 is going to be equal to the radical 3R temperature of the first gas over a molar mass of the second gas, or the first gas rather, and 3R T2 over M2. Because it's just really the speeds of the two gases. And so we can rewrite this as 3R times radical T1 M1 over 3R times T2 over M2. And so these cancel out, and what you're really left with is this value right here. And that value is going to be written as T1 M1 times M2 times T2. And that is exactly what we see over here. A lot of the times you don't see the temperature here, and that's because usually when you're doing diffusion questions, they are diffusing at the same temperature. But sometimes you do get some weird questions on this test where I guess the temperatures are different. So it's helpful to know that this is like the official big formula, I guess. Okay, that's all I have to teach. So let's do some problems. What state of matter corresponds to the diagram below? Other than the fact that the answer is literally right on top, you should be able to tell from like the diagram that these are farther apart. You see some collisions from the walls, and so this should tell you that this is going to be a gas, and it is in fact a gas. Problem 14: a sample of helium gas in a flexible container at room temperature exhibits a certain pressure. What will be the new pressure when the absolute temperature and the volume of the container are both halved? The pressure of helium will be... Alright, so let's first look at the temperature bit. We know that pressure is going to be proportional to temperature. So as temperature goes up, so does pressure. Because remember, temperature means how fast they're moving. And so if you're having collisions twice as fast, you're going to have twice the pressure. If you have collisions half as fast, you're going to have half the pressure. So as you have the temperature, you're also going to be having the pressure. On the other hand, pressure is going to be inversely proportional to volume. So if you double the volume, then that means you're going to have half the pressure. But if you have the volume, you're going to have twice as much pressure. And so if you have 1/2 pressure from the temperature bit, but twice the pressure from the volume bit, then that means the pressure is going to stay the same. And that is A, right here. So the answer is A, and we're correct. Let's go on to the next one. Consider the four gases: carbon dioxide, nitrogen gas, carbon chloride, and helium. Which is the correct order of increasing average molecular speeds at 100 degrees Celsius? So remember, the speed is going to be the root mean square velocity, so 3RT over the molar mass in kilograms. So as the molar mass goes up, your speed is going to be slower. But if you decrease the molar mass, you're going to increase in speed. And so basically we're looking at which one of these gases are going to have, like we're looking at the order of their molar mass from least molar mass to greatest molar mass if we're trying to go increasing average molecular speed. So carbon dioxide is going to have a molar mass of 32 plus 12, 44. Nitrogen is going to have 28. Carbon chloride, I have to look that one up. Carbon tetrachloride is going to be about 154, and then helium is going to be 4. So the increasing order, the correct order of increasing average molecular speeds, well, that means we're going to have the slowest ones first. The slowest ones is going to have the highest molar mass, which is going to be carbon tetrachloride. And then the next one is going to be the carbon dioxide, CO2. And then we're going to have nitrogen gas, and then helium. And so that is the correct order. And the answer is, I put B. This is the right this is the right order. Apparently I didn't write out I was too lazy to write out the answer choices. But yeah, this is the correct order. And it's because of this root mean square velocity formula right here. Let's move on to the next one. Which gas has an effusion rate closest to half that of oxygen gas at a given temperature? So if the effusion rate is half that, that means the rate of our gas X over the rate of oxygen is going to be 1/2. And so since we are at a given temperature, meaning temperature is going to stay the same, that means it's going to be the molar mass of oxygen over the molar mass of R. And so 1/2 is going to equal the molar mass of oxygen over the molar mass of our random gas X. That should be X, my bad. And so we know the molar mass of oxygen. We know it's going to be 32 over the molar mass of X. So let me just write that over here. 32 over mx. So 32 over mx is going to equal 1 over 4. And so if we do the math, it's going to be 128. And so which one of these is going to have a molar mass of 128? Hydrogen has a molar mass of 2. Helium has a molar mass of 4. This is not going to get 128. But xenon is actually has a molar mass of 128. So that means xenon is going to have an effusion rate closest to half that of oxygen gas at a given temperature. And we are correct. All right, we have a couple more. A sample of oxygen gas at a given temperature and pressure has a density of 1.30 grams per liter. What is it? Okay, whoops. What is the density of gaseous propane under the same conditions? Using that density, we can fill out a lot of information about PV equals nRT. So PV equals nRT. We don't know the pressure. We don't know the volume. Well, actually, we can just assume that the volume is 1. Let's just assume the volume is 1. And if the volume is 1, then that means we have 1.30 grams of O2 gas. And using that, we can determine how many moles of O2 gas we have by dividing by its molar mass. And so that's going to be about 0.0406. So N is 0.0406. R is going to be 0.08206. And then temperature is going to be constant. So between them, it's going to be constant. So that means P over T has to be equal to 0.0406 times 0.08206. And P over T, that means P over T has to be 0.08206, 0.0033. And it has some other stuff. How does this help us, though? If we know that pressure over temperature is that value, how does that help us relate that to gaseous propane? Well, we know that gaseous propane is also gonna follow this form right here. And so that means pressure over temperature is going to equal N times R over V. So N times R over V is going to equal this value that we got over here. And if we're trying to find the density, let's just assume we have one liter of our gas. If we have 1 liter, that means that N times R is going to equal 0.0033. And if we divide this 0.033 whatever value by R, what you're going to get is the number of moles that are in 1 liter. So let me just divide by that value. So that means we have 0.0406 and then some other stuff in 1 liter. So how many grams is this in 1 liter? Well, if we multiply this value by the molar mass of gaseous propane, propane, which is going to be 36.6 plus 8. So that's about 44. Yeah, I hope my math is right. That means the mass is going to be about 1.79 per liter, 1.79 grams per liter. And that is our density. And we're correct. So again, what we did was we found the P over T value of what we were given using the density. And so we could use that value to relate the number of moles times R over V to that same value. And if we're trying to find the density, we can just assume that there's 1 liter. And if there's 1 liter, we found out that there's going to be 0.0406 moles of propane. And we can turn the number of moles to grams to find the amount of grams per liter, which is density. Okay, we have one more question. A sample of gas measured at 20 degrees Celsius and 4 atmospheres is heated to 40 degrees Celsius at constant volume. Which statements are true of the gas after heating relative to its initial state? Well, let's go through them all, right? Number 1, the average molecular kinetic speed is increased. This does make sense. Remember, kinetic energy is going to be proportional to the temperature. And so if you increase the temperature, the average molecular kinetic speed is also increased. So 1 checks out. Number 2, the average molecular speed is unchanged. I mean, since we said 1 is true, then by default 2 is not true. 3, the pressure of the gas is increased to 8 atmospheres. Be careful here. Temperature is proportional to pressure, but the temperature needs to be in Kelvin. So really, we're going from 293 Kelvin to what, 313? Yeah, that's it. So really, we are going from 223 Kelvin to 313 Kelvin. So it's not like the pressure is going to double. Instead, the pressure is going to increase by a factor of this. So the new pressure is going to be this. And the pressure is 4 here, so there should really be 4. The new pressure is going to be this. So you have to be careful that that when you're doing proportionality and stuff, temperature is going to be in Kelvin. All right, let's take a look at number 4. The number of molecular collisions per second is unchanged. Well, the number of molecular collisions is going to be based on how fast the molecules are moving. And since we've already established that the number of the speed of these molecules have increased, then the number of molecular collisions also needs to increase. So no, it does not stay unchanged. Instead, it increases because we increase the average kinetic molecular speed. So that means the only one that makes sense is 1. And that is the correct answer. All right, that's all I have for today's lesson. I hope you learned something, and hopefully you'll join me for the next one where we're going to do some practice involving this entire unit.